Okay, so first off, you guys have drinks. Drinks over here. You come up, get your drink. You know, feel happy. Food over there. Step outside, eat it. Shovel in your face. I didn't get a chance to have lunch because I had a meeting. Intense meeting. So, everybody got it up? Good. First question. So, what are 4 things? Oh, you're ahead of oh. It looks like we're losing people. We're not supposed to be losing people, we're supposed to be gaining people. Yeah. Or yeah, chapter 1. Chapter 1 quiz. Quiz number 2, chapter 1. Yes. Get it? Still trouble? Your Wi-Fi is not working?
There's a AT&T issue going around in
AT&T issue?
And Verizon.
Okay, so you took a picture of it? Yeah. I'll let you upload it later. Okay, good job. Okay, so what are 4 things that you must wear when working with chemicals in the lab?
Lab coat, safety glasses, closed-toe shoes, and gloves.
Okay. Do everybody agree with that?
Yeah.
Anybody disagree with that?
I did like hair ties.
Hair ties. Oh, that's a good one. Yeah, that is a good one. I'll give it to you. Yeah. Okay. What is micro, macro, and particulate? Yes.
Can be seen with an eye. With human eye.
Macro?
Yeah.
Okay.
And the micro cannot be seen with human eyes.
Okay, what do you need to see with it?
Microscope.
Microscope, okay.
What is it?
Particulate?
I think it's too small, cannot see it.
Okay, yes. So you'll need a special instrument to see it, or you have to use symbolism or symbolic means. Anybody dispute with that? Everybody got that one, right? It's cake so far, right? Okay. So what is the starting point of scientific method? Sorry about the lighting. I need to get a little shade so you guys can really see all my writing. Starting point of scientific method. Where do you start at? What was that? Creating hypothesis. What was that? Forming a hypothesis. Okay, now go here. You already answered that. What was that? Question. Why? So it's not the question. There's one more before it. Anybody?
observation.
Observation. That is correct. Yes, observation. First, you gotta say, "Oh, the sky's blue," right? And then you say, "Why is the sky blue?" Right? Okay. Did everybody get it right? No. Anybody get it right? No. You got it.
Yeah.
Okay. So we were talking about the 3 phases of matter. You guys remember the 3 phases? What were they? Without looking up there, I know they're out there.
Gas, solid, liquid, and in some cases plasma.
So we have gas, solid, liquid, and our 4th phase is plasma. Okay, so what is the distinction? What is the distinction between solid, liquid, and gas? take into consideration we're talking about water. Water would be which phase? Would be liquid. How does that differ from ice? Solid. Ice is a solid, okay? But what is it that makes a solid solid and a liquid a liquid?
How quickly the particles can move?
How quickly the particles can move. That's actually really good, yeah. Really good, good answer. Okay, so, and we know that we have a gas, right? So I'm gonna add one more. Okay, so can you guys see that? So how do I go from a gas, from a, let's say a solid to a liquid?
Increase the temperature.
Increase the temperature. So by me increasing that temperature, what's happening?
You're making the particles move and accelerate.
That's right, the particles are moving, and as a result of that, we're getting melted, right? So it's that concept of movement, right? So that kind of gives us this next term, the kinetic molecular theory, right? So theory, we talked about theory already, right? So kinetic means what? Move, right? So we says kinetic molecular, molecular means molecule, right? Okay, so the kinetic molecular theory is the reason that we can go from phase to phase. Now, are we changing the composition of water, right? Are we changing its chemical form?
It's the water.
Still water, right? So it's still H2O. So that's not changing. So the only thing that's changing is the fact that it's moving, right? So if I go from liquid to gas, I'm just moving faster, right? Everybody agree? Okay, cool. So it's kind of like, have you guys ever been on a beach where it's really, really hot sand? Yeah. Yeah. Okay. So you see the water there, and you're on that sand. And you have no shoes on. Are you walking slowly to the water, or are you running to the water? You're running, right? So it's because heat causes us to move a little bit faster, right? We're either trying to get to that cold place and kind of cool us off, right? So that's the same case in terms of a compound or a molecule, right? So we can go from that transition of being a solid to a liquid by increasing temperature. But it helps speeds up that process. Those molecules are moving. So, have you guys heard of absolute zero?
Freezing point, right?
It is a freezing point, yes. Absolute zero is a freezing point of what?
Celsius.
Not Celsius.
Kelvin.
It's in Kelvin. So it's 0 degrees Kelvin, right? That's the temperature. I'll write it on the board here in a second. Or on the board over there in a second. So at 0 degrees Kelvin is absolute zero. But what does that mean? What does that freezing point mean?
There's no movement of particles.
Okay, so at absolute zero, there is no movement of particles.
Zero means that there's no energy in rotation.
Because there's no movement of particles, right?
Yeah.
Okay, so okay, so that's 0K. Kelvin is a unit of temperature. It was established so that we would have absolute zero, which just happens to be equal to negative 273.15 degrees Celsius. Okay, what is room temperature in Celsius? Anybody know?
28.
20, well, here it's probably like 30, but yeah, so 22 normally is what we have at like 72 degrees. Right, 72 degrees, about 30, 35 degrees.
That's way too hot.
No, it's about 22, 30. Yeah, it's about 22, 23. 72 degrees is about 22, 72 degrees Kelvin. I mean, Fahrenheit is about 23 degrees Celsius, roughly. So 30, let's say 96.5, what is our temperature? 96.8. 96.8 is our body temperature, right? So that is 35 degrees, or 37 degrees Celsius. Okay, so Kelvin is going to be that 0 degrees Kelvin, it's going to be negative 273 degrees Celsius. So if I'm converting from G Kelvin, Celsius to G Kelvin, I'm just going to be adding 273.15. Okay, so temperature in Celsius plus 273.15 equals our temperature in Celsius. Okay, so an equation already. Just got started. Already equation. Okay, so the key is that we know that particles stop moving at 0 degrees Kelvin, right? Absolute zero. Okay, so we also know that what is that point where we're going from solid, say solid to gas? That's called the what point? What was that?
The boiling point.
It's the boiling point. Okay, so a boiling point is the temperature. Just throwing definitions out there. Oh, you guys can see over there. I knew I'm getting exercise, going back and forth. Stop this one. Third grade handwriting, let me fix that. So. So. Okay, so that process, we're going from a liquid to a solid. It's called what? Freezing. Okay, so this direction. Okay. The process of going from a solid to a liquid. Melting. Process of going from a liquid to a gas was boiling. Well, we have another term as well. Melting, because we know that that's from solid fluid. Right? So if we're going from a liquid to a gas, there's another term.
Evaporation.
Evaporation. Okay. This direction. So the process of going from a gas to a liquid. Not necessarily cooling. What was it? Condensation, that's right. Okay, the process of going from a solid to a gas. There's a band of old, I think it was 90s or 80s, 90s, in the 90s. Kind of reggae-ish, reggae pop-ish. Starts with an S.
Sweat.
Not Sweat. Although that would be a cool name for a band.
That would be.
You guys heard of Sublime?
Oh.
Sublimation.
Oh.
Okay, process of going from a gas to a solid. Probably haven't heard this one. Deposition. Positive deposition. So freezing is also called. Okay. Okay, now, hard question. So we just talked about it takes temperature to make that happen. So how do we make temperature change? What do you use to make temperature change? So you said a heat source. What do you mean by that? Resistance? Is it just resistance alone? So if I just put a resistor there, it's going to work? So kinetic energy. Ooh, kinetic energy. So we could do it with kinetic energy. Yeah, that'll definitely work. Right? So if we have energy, right? Because that's what you're basically getting at, is that energy. So it takes energy to go from that transitional state, right? It takes energy to get there. It doesn't just happen on its own, right? So either it's like solar energy, it's, you know, when you set a resistor, it's not just the resistor alone, right? So you need some friction going through that resistor, right? You need some electricity or something flowing through that resistor so that it'll allow it to get heated up, right? So this process takes energy, right? So, but again, are we changing the state of things? Is it still water, whether it's steam, or is it still H2O, whether it's steam, water, or ice? It's still H2O. So that is called a physical change. So the change in state is a physical change. Everybody agree? Okay. So since it is a physical change, everybody got this down? And you got the fact that it takes energy, right? So this is just basically showing you all the different states. and kind of some characteristics of it, right? So we know that solid is going to be rigid, right? It's not going to be able to change its volume or its shape. It's going to be set because it's frozen, right? And then as soon as it starts melting, that whatever it is, it melts. Then it's able to sit there and change the shape of the volume. But it's only, if you notice, it's all at the bottom, very bottom of our container there. You can see that. Still batteries. Tell it's a Monday. There we go. That's working now. Okay. And so as we heat it up a little bit more, gas is going to occupy that entire container, right? Whatever it's in. That makes sense, right? It's kind of like this. So if, let's see, Juan, pick on you. So if Juan toots, right? So Bart, you know, is it just going to stay where Juan is at? What's going to happen to the fart?
Spread.
It's spread. So that spread is called diffusion, just so that you guys know, right? So it's going to diffuse, and it's going to occupy the entire room, right? And so Juan is going to be smart. He's going to look around. He's going to be like, who did that, right? And then everybody's going to be looking around like, who did that, right? As they smell the fart, right? So because we know that the gas is going to be able to occupy that full room, right? And why is that gas going to be able to occupy that full room? Why? Why? I just want attention. That's why. Anybody?
Starts to expand.
Is it that gas expands? Good. Okay, so we know gas, that's one of the characteristics of gas, that it's expanding. But is that gas molecule expanding?
No.
No. So gas as a whole is expanding, right? But what's happening? So we're saying the volume is increasing. Okay, so this volume is increasing. Why? What is it doing? What is those molecules, each individual molecule doing?
Attaching different.
Is it attaching to anything?
No.
Because it was attaching to things that would stay together, right?
Yeah.
It's spreading out. But why? Why is it spreading out? What's that? I hear it over here.
Because it's a gas.
Now you're going in circles. Not because it's a gas. What did we talk about earlier? It's diffusing, but why is it diffusing? That means what's happening?
It's breaking down.
Is it breaking down? So you're telling me you just broke the rule, right? You just told me that H2O is H2O, like it is, right? Whether it's
Energy.
energy, okay, because of energy. And then what happens when you put energy into something? So what happens if I just decide to shock you with something? Are you just gonna sit there?
No,
so it increases with energy, which.
Okay, I'm gonna get a counter product. Anybody got a counter product tomorrow? Or like, what is that?
Tasers.
Huh?
Taser?
A taser. A taser. Anybody got a taser I can borrow?
No.
No? Nobody got a taser I can borrow? Darn it. Okay, so if I zapped you with a little bit of energy, what are you gonna do? Are you just gonna sit there as nothing happened? No? What are you gonna do?
React.
Did you move? So you're gonna move a little bit, right? So what do you think is happening as we put energy into those molecules?
They start bouncing off other.
They're gonna start bouncing off of other molecules. They're gonna speed up, right? They're gonna move, right? So if I put a little heat under your seat, are you gonna stay in that seat? Well, it depends. I guess. Put a lot of heat in that seat. Are you gonna sit there, right? So I know what to do. I just put a lot of little shocks to see if I can get you guys to move, because you ain't moving, right? So we know that molecules are gonna be moving. They're gonna be constantly moving, right? We already know that. But as we speed up, or as we put more energy in, they're gonna be moving faster, right? And as you guys will move faster, somebody keeps considering shocking you, you're gonna move faster. You're not gonna sit there and walk slowly or anything like that. As somebody zip, 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 zip. As I put energy into you, you're gonna move faster, right? I would hope so. Okay, so that's the same thing that's happening. So those molecules are going to be constantly moving, and they're going to be moving faster. So as we change from states, from a solid, they're going to be moving like this, you know? Have you guys ever been to a nightclub where it's really, really packed?
Yes.
Yeah.
Yeah, and so you don't have any room to move. So you're doing this, you're doing looking cute, right?
Yeah.
And you're not sweating or anything like that. You're just there looking cute, right? And then as soon as you get a little room, you're starting to move a little bit more. So that's kind of like the liquid, right? Hey, you can do the line dance together, right? And then when you have the whole dance floor, then you can be doing, you know, and all of this all over the place, right? Because now you have that energy to speed it up, have that room to do it, right? So plasma. Plasma is kind of a weird, it's kind of a weird state, right? It's that gaseous state, but it also has a certain amount of charge associated with it. So in a sense that it's kind of like a state that's storing a little bit of energy, right? And so if you guys think about your stars, lightning, right? Those are all examples of plasma. Those plasma TVs that just take up all the damn energy that we see, right? Other examples of plasmas, right? So, but it's a kind of very unique state. But the key thing is that it's kind of like gas, but it's kind of not like gas, right? Because it's able to maintain that charge. Okay, so here's an example. We have a plasma torch. Okay, so weight versus mass. So mass is going to be the amount of matter of an object. The weight means that there's gravity that's going to be exerted on it. Now, you think about this, right? Think about it. So, am I going to weigh the same on the moon and on Earth?
No. The gravity is different on the same unit as on Earth.
That's right, because the gravity is different on the moon, on the Earth. You said it's less, actually. That's right. So, is my mass the same on the moon and on the Earth?
Yes.
Yes, it is. Why?
Mass didn't change, but the weight did due to gravity.
That's right, because mass is not dependent on gravity, where weight is dependent on gravity. See the distinction? So, law of conservation of mass. So I'm just going to tell you this. Law of conservation in general, right? Law of conservation basically means that what you put in is what you get out, okay? At the end of the day. Okay, so in terms of a chemical reaction, that total amount of stuff that you put in should be exactly the same amount that you get out. So at the end of the day, if you're collecting everything and you didn't lose anything, it should weigh exactly the same as a total, right? Now, you could get changes. That could be a chemical reaction, so you get partner switching and all that stuff, or you could just get physical changes, right? So at the end of the day, if I collected all of the steam that I got from an ice cube as I heated up that ice cube, it should weigh exactly the same as the ice cube initially, if I collected it, right? So if I condensed it back down, froze it, it should weigh exactly the same if I didn't use it. Does that make sense? Okay, so that's going to be true. The law of conservation is going to be true regardless of whether it's a chemical reaction, a chemical change, or a physical change. So here's an example of this. So, I wish I could probably tell you a little bit about this. You know, he was brewing this this year. Was it? Or not this year? It was 2 years ago. Oh,
Last 2 years.
Last 2 years. Last 2 years. That's right. Okay, you did it too. So as we go from they call it pre-beer, right? Pre-beer is basically you have hop, sugar, and the water and yeast, right? So at the beginning, what you get there should be exactly the same weight that you should get out. Even though you're producing at the end, beer is just going to be basically alcohol. You may have just a little bit of sugar left, right? You're going to have carbon dioxide. At the end of the day, it should be exactly the same weight that you get out at the very end. And that's what you're kind of seeing here in this diagram. That's what it's showing you. So we start off with sugar. We end up with carbon dioxide and ethanol, alcohol. Okay. So that's the same thing here. If we look at a a car battery essentially. So, which is made up of lead and lead oxidized plates. And we have our acids. At the end of it, when your battery is pretty much dead, you end up with lead sulfate, lead 2 sulfate, and water. Right? So in both cases, you end up with exactly what you started out with in terms of weight. Right? Because the law of conservation says that what you put in, you have to get out. Okay? And this works on multiple forms. If you take a look at what you put in, you had lead 4 oxide, and you had sulfuric acid. What you got out was you're getting lead 2, sulfate, and water. If you take a look at the components, they're exactly the same. You're not making anything brand new, right? So if you take a look at the elements, you're not making any elements, right? You're just switching up partners, right? You're mixing it up. Okay? You guys are clear on that? I'll give you guys an example. I'll switch the screen this time early. So, all right, go to the floor. So it's not twice the amount of work. It's not for you, it's custom. Okay. Okay, so let's talk about respiration. What's respiration? How many of you guys took bio? Everybody took bio? Okay, everybody took this. Okay, good. So I have at least 3 people who took a bio. They're raising their hands just like this. Okay, so respiration. What is respiration? Breathing. So when we breathe, what are we doing chemically? We're taking in air. What type of air are we taking in? Is it just any type of air? No, all the time. Well, we're taking it all the time, but are we using it all the time? No. What are we using? Oxygen. Okay, does anybody know why we're taking in oxygen? This is the chemical formula for oxygen gas. It's a diatomic. So we have to put a 2 here. This is called a subscript. Okay. This here is just letting us know that it's a gas. Okay. Why do we take in oxygen? Why do we breathe oxygen? Anybody who took bio? Anybody who didn't take bio? Why are you breathing?
It's our fuel for our muscles.
Is it? Is oxygen just a fuel for your muscles? You need something else. It's actually a chemical reaction. Wait for a reason. Other than just to stay alive. I don't take a guess.
Do we exhale carbon?
So we exhale carbon dioxide. So this is called the yield sign. That basically means that we're making whatever it is. So one of the things that you're making is carbon dioxide. The byproduct. Okay. This is the formula for carbon dioxide. And we'll put a G here, gas as well. Okay. So we breathe in oxygen, we make carbon dioxide. So obviously something has to come from carbon because otherwise we could get carbon outside of the reaction. So something else that we need to take in has carbon in it. Okay. How many of you guys celebrate Thanksgiving? Anybody? So if you guys notice during Thanksgiving, you're eating, you're like, and you have to take that deep breath, you're like, and then you blow out, right? And then you start eating, okay? So typically what you're trying to do is you're taking in some type of carbon-based molecules. 6H12O6. So this is glucose. Glucose is the ideal thing for us, right? Glucose is a sugar, right? It's the perfect source of energy for us because glucose gives us 32 ATP. He was talking about that energy. We call it cellular energy. We use ATP for cellular energy, right? Now, it's another byproduct of another reaction, so we're not going to take it into consideration right now, but just know that you get that 32 ATP at the end, right? Actually, it's 36 to 35, depending on how you count it. But at the end of the day, you're also going to have to go pee, right? After you eat that big meal, you have to go potty, right? You guys remember that? Yeah. So we're going to get H2O. Okay. Now, this is the chemical equation for cellular respiration, right? Now, I'm going to tell you, it's not a balanced chemical equation. So this is what your cells are doing. Your cells are getting that oxygen, they're breaking down that sugar, they're making carbon dioxide and water, and then we'll put ATP. Okay. Again, this is not a balanced chemical equation. Now, what do I mean by a balanced chemical equation? The law of conservation says that what you put in, you have to get out. Okay. So again, these guys are called substrates. Right? They let us know how many there are of that particular atom in that compound. Right? So this guy has how many carbons? This guy has how many oxygen? Okay. This guy has how many carbons? This has how many hydrogens? Okay. So now the law of conservation says that what you put in, you have to get out. Okay. So that basically means that we have to keep track. We have to bookkeep. Because at the end of the day, what we put in, we got to get out. So let's count how many carbons are on this. Is called the reactant side of the equation. These are your reactants. So this is saying glucose plus oxygen. That plus means and, right? Glucose and oxygen makes carbon dioxide and water. Okay? And these are called your products. Ready with me so far? Okay. On our reactant side of the equation, how many carbons did we say we have? How many hydrogens do we have? 12. And how many total oxygens do we have? 8. But we have 6 plus 2. Okay. On our product side of the equation, how many carbons do we have? How many hydrogens do we have? And how many oxygens do we have?
3.
3. 2 plus 1. Okay? So now you don't have to be a sharpest knife in the drawer, but you can clearly see that 6 and 1 are not the same number, right? And I told you the law says that what you put in, you've got to get out. So we need to set up and change what we call the coefficients. Coefficients will be the numbers that will be in front of you. Okay? Now this tells us that we have this many glucose molecules, and this many oxygen molecules, and this many carbon dioxide molecules, and this many water molecules. Right? It tells us about the entire thing. Okay? So the coefficient means you're talking about that entire compound, that entire molecule that's after it, that entire element. Okay? So we need to adjust it so that we can have a balanced chemical equation. So for instance, we have 6 carbons on our reactant side. So what can I put in front of the carbon dioxide so that I would end up with 6 carbons on my product side? 5? 6, because you're multiplying it by that 1, right? So if I put 5, it will be 5. Okay, so it needs 6. So now I have 6 carbons. Okay. Now what can I put in front of the hydrogens so that I end up with 12 hydrogens on my product side? So I have 2 now. Now remember, you're multiplying it with the number that you have in front of here. You're multiplying it by that number 2. 6. So then that would give me 6 times 2 is 12. Because you're saying that you have 6 waters. So you're saying H2O, 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 H2O. Right, so that would be 6. Right, so that's 2, 4, 6, 8, 10, 12, right? So that's what we're saying by having that coefficient. Yeah, 6 waters. You guys see that? Just have that look. So what you guys? So now we have 12 H2Os. Now we have to calculate how many oxygens we have. So if I have 6 times 2, that's what? 12. Okay, so that's 12 plus 6 times 1. So that's a total of 18. Okay, so we come over to the other side. I have 6 here. My carbons are good, so I'm just going to check those off. But my carbons are good on both sides, 6 and 6. Right? Everybody would agree to that? Check out that. My hydrogens are good, 12 and 12. My oxygens are a hot mess. I have 8 and 18. Okay, so I know I'm getting 6 from here. I don't want to change those, right? Because they're already set. So if I take 6 from 18, 18 minus 6, what's that? 12. Okay, so 12. So what can I need, or what do I need to put in front of my oxygen so that I would end up with 12 oxygens? 6. If there's no number in front of it, it's understood to be a 1. Okay. So we do the math. 6 plus 12. Is that equal 18?
Yes.
Yeah.
Okay. So would that be balanced? That's a balanced equation. The way I always remember this is a standard one. This is one you're going to see the rest of your life. If you guys do photosynthesis, if you guys do cellular respiration. Photosynthesis is the reaction, the reactants and the products are mixed on the other side. Okay. Sugar is the devil. Glucose, 6, 6, 6. All right. Sugar is the devil. Okay. So what you put in is what you get out. Now this pertains to the mass, right? So if we calculate all of that mass that we put in, we have to get that mass out. Okay. It also pertains to the number of each element that we have in that reaction. Okay. And it also pertains to the energy, right? We have to account for the energy that's being broken. One side is going to be breaking bonds, one is going to be gaining bonds. As a result of that, we're going to get energy release. It has to be accounted for. So at the end of the day, it's checks and balances. Everybody got this? Feel confident? Want to try another one?
Yes, sir.
Yeah. This is also considered to be a combustion reaction. A combustion reaction basically requires oxygen to be present, and you're making carbon dioxide and water. Let me give you another combustion reaction. Okay, so first thing that we always want to do is figure out how much we have on our reactant side and on our product side of each of the different elements. Okay, so what are the atoms that we're working with? many hydrogens do I have on my reactant side?
4.
How many hydrogens do I have on my product side? How many oxygens do I have on my reactant side? And how many oxygens do I have on my product side?
3.
How many carbons do I have on my reactant side? And how many carbons do I have on my product side? So, balanced. Okay, what do I need to do to balance? Carbon is looking good, right? It's 1 and 1. Okay.
Add 1 salt.
Add what?
1 salt.
What do you mean by add 1? Well, you can't just, okay, so some rules, another rules. You can't just throw an oxygen in there just to make an oxygen, right? Remember, you can only change the coefficient, right?
Okay.
So we need to find a way of changing the coefficient so it balances out on both sides. What was that?
Added 2 in front of the hydrogen.
In front of, on the reactant side or product side? Okay, so we're going to add a 2 in front of the water, right? So that means it affects all of the elements that are in water, right? Or all of the atoms that are in water. Okay, so that gives me how many hydrogens now?
4.
Okay, and then in terms of the oxygens, I have 2 here, and then how many do I have over here?
4.
2 times 1 is what?
2.
Okay, so 2 plus 2 is 4. That's what you're saying, you're adding them both together. Okay, so is that balanced?
No.
No, what do I need to do?
So 1 oxygen.
2.
Okay, so what do I need to put? Put 2 there?
Yeah.
Okay, now is it balanced?
Yes.
Okay, so now that's a balanced chemical equation. Okay, so are you with me so far?
Yeah.
Okay, good. So I'll throw one more for party, right? Okay, good. One more for the party. Oh, let's do this a little more challenging. I'll also stick with combustion reactions. Bring up with okay, this guy is called phosphorus. Okay. What is the first thing you want to do? I want to count. So you write down my elements, or atoms. Okay, on my reactant side, how many carbons? On my product side, on my reactant side, how many hydrogens? On my product side, 2, right? Okay. On my reactant side, how many oxygens?
2.
And on my product side,
1.
3. Okay. So, balanced? Nope. What do I need to do to balance it?
Carbon.
Okay, so look at a carbon. We have 2 here. We want to get 2 here. So what do I need to do? What do I need to put in front of this carbon?
2.
So we got 2 carbons. Okay. So how many? We'll do the tally here. Okay. Now what? So 2 times 2 is 4 plus 1. So now we got 5 oxygens. We balance that. 2 and 5 for balance? No, but the carbons are good right now. Okay, so we'll leave the carbons alone for right now. Okay, hydrogens. What do I need to do to balance out hydrogens?
You get 6 on the right.
I need to get 6 over here. So 6 here, you said?
3.
3.
And
Yeah.
3.
So you need times it by 2. No, you need 6.
Okay, that gives me
Oh,
6.
yeah.
So that gives me how many oxygens?
8.
So I have 2 times 2, 4, right? Plus 3 times 1,
7.
7. Ooh, that's a nasty number. Okay, so when you get a situation like this, there's a couple of things you guys can do. You can just randomly try to guess and try to make it work, or you can take a look at what you have, right? So we have 2 oxygens that are only coming from the air, right? So you're always going to have 2 oxygens coming from there. So if I have 7 here, right, and I want to get 7 here, what can I multiply it by so that I ended up with 7?
Okay, 7 on
7.
right now.
7 times 2 is
14.
14. But what can I multiply it by? Somebody said 3.5 or 7/2, right? Guys, we know that. Guys, remember fractions? 2 times 7 over 2. These are going to cancel out. It's the same thing, same time. 1. So I end up with just 7. Right? So if I multiply that by 7/2, then it's going to work. Now here's the problem. Now if I'm looking at a single oxygen molecule, right? Or we'll just make it like people. Okay. So if I decide to cut Raul in half, is he going to be okay? Is he?
Feel different.
Well, I don't think he's going to be okay. So if I cut him in half, right? He's not going to be okay, right? If you cut a molecule in half, a single molecule, it's not going to be okay, right? So what we have to do now is multiply the whole equation to get rid of that denominator. That denominator is what?
2.
2. So I need to get rid of 2, right? So I multiply everything by 2. Okay, so then I'm going to end up with, I'm going to write it above it, if that's okay. That's 1, 4, 2, C. Okay. Everybody with me?
You distributed the 2.
That's right. That's it. Okay, questions? Concerns? Anybody want to give me cash? Take millions still. Okay, good. Okay. So you guys just learn how to balance chemical equations. This is something that we're going to be learning later on, but you need to know it now. And you guys are ahead. Okay. So we need to start talking about elements. Elements are basically pure substances. They're pure, right? They can't be broken down to anything else. So oxygen, gas, O2, this is considered a diatomic element. there are 7 diatomic elements. What that means is that under normal circumstances, under normal conditions, these elements like to have 2 of them, right? So you have 2 O's. So your diatomic elements are going to be oxygen, nitrogen, so we have hydrogen, oxygen, nitrogen, fluorine, iodine, chlorine, okay? So those are the 7 diatomic elements. So the way I remember it is, have no fear of ice cold beer. Okay. Okay, so you also take a look at your periodic tables. Everybody has their periodic table available. If you take a look at it, it forms a little 7. You have nitrogen, oxygen, fluorine, and then chlorine, bromine, iodine. Forms a 7, and then there's the hydrogen on the side. Let's see that. So, diatomic. So again, diatomic basically means di meaning 2 atoms. Okay, so it has 2 atoms, elements. So an element again is going to be a pure substance that can't be broken down chemically. So you're getting those pure elements. So we have an example of that would be sodium. Sodium is an element, but it's not a diatomic. Sulfur is an element. That one is actually a polyatomic. Phosphorus is also a polyatomic element. We'll talk about the numbers that they have. Okay, so right now, currently, there's well over 100 elements on the periodic table. You guys can see that, right? There's like 118 that we have known about. There's probably even more since then. Right? 90 of them are naturally occurring. Naturally occurring, meaning that they're found in nature. The other ones aren't found in nature, we make them. Okay. So, as of right now, there's 118 that are being made. One more than a dozen. I'm struggling today. Okay, now you'll notice on your periodic table, you guys on your periodic table, you have those that are like in white, and then they have parentheses around their, and that's that number. It's going to be what you see in parentheses. That one is going to be its atomic mass, right? Or its atomic weight. Okay. So it's in parentheses because they're not 100% sure about it because they haven't been able to balance out the number of neutrons with the number of protons to keep it stable long enough. So they put it in parentheses. They're still working on it. So again, that's an example that is a man-made atom. Okay. So if you guys take a look at your periodic table, you'll notice on your periodic table, you have these guys here at 57. We'll say 57 to 71, right? Those guys are down here, right? You guys also have the same thing. Now, what that means is that this spot here is a placeholder, right? You guys don't have anything there. You just have an empty spot on your periodic table, right? Because that's a placeholder. So what the periodic table really looks like is like this. Okay, so it really looks like this, where you have that, those that were down here at 57, 71, actually filled in between this row and that row, okay? So the reason why they take them out on your periodic table is so it fits on a piece of paper. Otherwise, it wouldn't fit on a piece of paper. Okay. So we want to keep that in mind when we start talking about electron configuration, which will happen, unfortunately, at the end of the semester. Okay, so atoms. So atoms are going to be the smallest particle of an element. Okay, so in the case of oxygen gas, O2, which is the diatomic element, the atom would just be oxygen. So it would just be that element. Okay. So they can be individually by themselves, like sodium, or they can be combined with things like sodium chloride in terms of a compound. Okay. A molecule is going to be two or more atoms that are interacting, that are bonded in some way. Okay. Now, you notice I said two or more. I didn't say two or more different, right? So for instance, oxygen, which is a diatomic element, is also a molecule. Okay. So it's just two or more. Now a compound is going to be two or more different elements that are bonded. Okay, so you guys take a look. This is hydrogen gas. These are hydrogen gas molecules, but they're also hydrogen gas elements. Okay, because they're a diatomic element. This is oxygen gas molecules, which are also oxygen gas elements. Now phosphorus likes to have 4 for stability, right? So it's considered to be polyatomic. Poly meaning more than one, and poly meaning more than two, right? So polyatomic, okay? And then sulfur likes to have 8. They hate sulfur. Okay, so all of these guys are considered elements. All of these guys are considered to be molecules, right? Because the definition of a molecule is what again? It's 2 or more, right? Okay. So let's see. Now, water, H2O. We got 2 or more elements. Okay. Water, carbon dioxide, glucose. Oh, we just talked about, right? Wow, imagine that. So those guys are also considered to be, are they elements? No, they're not, because they're not pure, right? Okay, so there are molecules though, right? As I said, two or more. Aren't these two or more?
Yeah.
Right? Okay, so they're definitely molecules. Now these are also compounds, right? Compounds are two or more different elements. Okay, you guys got that? Piece of cake? Two or more different elements. Okay. So an element can be a pure substance. A compound can be a pure substance. Like for instance, if I have pure cane sugar, right? From Hawaii. Okay. So that's pure. They're all sugar molecules. They're all the same sugar molecule. Right? Pure basically meaning they're all the same. An element, oxygen, that's a pure element. Oxygen gas. If you only have oxygen there, it's pure. If I only have gold there, it's pure. 24 karat gold, pure gold. That's all that's there. Okay? So a substance can be pure, even though it has different elements in it. Okay? So you got a test right here. Put a couple things on the board. Maybe we'll take a quick break. I'm getting tired of being up here. Okay, P4, which is phosphorus. Is that an element? How many people say it's an element? Raise your hand. 1, 2, 3. Anybody don't think it's an element? Hey, got to vote. You don't think it's an element?
Well, I mean, it is, but it's a molecule, right?
It is, but can it be both?
Sure, yeah.
Okay, so can it be, first off, we're deciding it's an element. What was the definition of an element? It's pure, right? Pure meaning, in this case, we're meaning exactly the same ash, right? Okay, so yes, this is a pure. Okay. Sodium in it. That an element? Sodium chloride, is that an element? No. Okay, and ozone. Yeah. I say no. Why? If we base it on the definition, it is, right? So we're going to put a check here. Based upon the definition, it would fall into the category. Okay. Come back to the definition. Okay, compound. So what compound? What is the definition of a compound? So what do you think the definition? Is it two or more? Is it just two or more? What was that? Say it again. two or more different. Okay, two or more different atoms. Are there two or more different atoms in P4?
No.
Okay, so we know that this is a no. Okay, what about sodium? Two or more different atoms? What about sodium chloride?
Yes.
What about O3? Okay, molecule. Definition of a molecule. Two or more. Okay, two or more atoms. That's it, right? They don't have to be different. Okay, so P4. Sodium, Na. No. No. Sodium chloride.
Yes.
Yes.
Yes. Right, because it's two or more, right? That's one, that's two. O3. Okay, this cake. Now it's going to be important that you realize this, right? Because it kind of helps us categorize things, right? And that's going to be important later on. Okay, so let's go ahead and take a 10-minute break. Go relax a little bit, go get your drink on, do what you need to do, go potty. You know, call your girl, let her know you're alive. Boy, let her know you're alive. Let him know you're alive. So, your lab reports. There are changes that I need to make, so I want you guys to sit there and sit this around, let it around. But you guys have a formal lab report. Today, we're going to work on writing that lab report. So that's going to be part of your lab. The other thing that we're going to work on is dimensional analysis. We're going to kind of go out of context. We're going to just get the ball running. So you should have, today is going to be a dry lab. On Wednesday, it's going to be a wet lab. I switched the days because it gives me enough time to make sure I have everything in place and ready. And I usually have crazy meetings on, well, I have crazy meetings on Mondays and Wednesdays, but one on Mondays is typically more crazier than So you have 4 formal labs. So you make one write this in your lab report. 4 lab reports that you have to write us for scratch. Just 4. The first one is the Mentos, and we'll be doing that one together. So you guys know how to write a formal lab report. Your second one, I'll let you know what your second and third report. So we'll say formal lab report, and in addition to it, where it says 100 points, I want you guys to cross out that 100 points. It's actually going to be worth 300 points. Okay. So if you think about it, that's 4 lab reports that are going to be worth a total of 300 times 4, 1,200 points, right? Which is almost as many labs as you have. So each of your labs that you guys are turning in are worth 100, right? So that first one that you did was worth 100. Now the report for it at 300 points. Okay, good. Okay, so you have a title. So of course I need to know the title of the lab. Okay, so you multiply that by 3, so it's going to be 15 points for the title. Okay, 15 points just for putting the title of the lab, so it is correct. I expect these to be typed. Okay. So you want to write that down, has to be typed. Because I have 3rd grade handwriting, I can't do my own handwriting half the time. I know that I can't read your handwriting, Kevin, some of the time, so make sure that we're able to sit there and do that sometimes. Purpose. You guys know what the purpose is? What is the purpose of this class? To learn, yeah. The purpose of this class is to learn, right? So the purpose is just basically what is the purpose of the experiment that we're doing, okay, in general, or the problem that we're investigating. hypothesis. You guys know what a hypothesis is. So what was the hypothesis of the experiment that we did the last time? Some of your guys' hypothesis.
Will the soda change colors after pouring the Mentos in?
Would the soda change colors after pouring the Mentos in? What was the answer?
For the water, yes. Or for the Cokes, too dark.
Too dark. Okay, and then data / observations. You guys know what data and observations are?
Collect data and you make observations based on data.
Okay, or you can collect observations and have results based upon those observations. Right? So data and observations are things that you're collecting, things that you notice. Like you noticed that the water changed colors where the Coke didn't, right? So those are observations that you may note. Okay. What were some of the observations that you guys made during the Mentos experiment?
High up the phone.
Okay. Okay. That would also be data, right? Okay. So data collected is what is collected. So how high it went up, that would be data, right? So observations are just kind of globalists, right? So both of those fall in the same category. It's just what you're writing down, right? So here, this is the one point where I do want your beautiful handwriting, right? I want you to take pictures of the data that you guys collected, right? In your data and observations and the observations that you took. Because it helps me, even though half the time I can't read what you're saying, it helps me see that you were actually there doing the experiment and you were taking those data, right? Or those observations. Now, results is your data prettified. It's answering that question. It's showing how it does answer that question. Like, for instance, he says he would simply show. He had a picture of his Coke, he had a picture of his water, and he had a picture, a nice little picture showing them all together, showing me that the water changed colors where the Coke didn't. Okay. So that would be an example of results. And he could explain it. That picture would be explained. Underneath it, you would explain the results. Right? Because you want to help your reader understand what you're trying to say. Also, in your results, you're going to have your calculations, the calculations that you guys have to do, right? And you're going to have your beautiful tables and your graphs, right? That falls under your results. Right? It's where you're showing your data, you're displaying it so that people can understand what it says. And you want to guide them through it, okay? A good scientist helps the reader go through their results. Through the data, but through the results. Okay?
Is it also typed?
Yes, results should be typed. Yes. So the data part is the only part that doesn't have to be typed. The results need to be typed. The tables, every one of your tables should be labeled. They should have a little diagram or a little commentary of what I'm looking at. Right? So your conclusion. So in your conclusion, it has multiple parts. First part is that you want to briefly restate the purpose and your hypothesis. So if I get lazy, what I do is I go to your conclusion and it tells me everything I need to know, right? Then you want to evaluate your hypothesis. What do I mean by that? If you're right or not.
Yeah,
that's right. If you're right or not. Okay. Was it right? Was it wrong? Why? Why not? Okay. And then if there were any questions that needed to be answered in the lab, you want to sit there and answer those questions. Make sure everything is answered. If there were unknowns to be identified, you want to make sure that you identify those unknowns, and make sure that you give me, let's say, a number to that unknown. Like, for instance, there's going to be a point where you're going to have to identify a metal, an unknown metal that you're working with, right? And so you're going to tell me, oh, my metal was unknown number 17. Unknown 17 is iron. Okay. So that's what I mean by that. In this case, was there any unknowns?
No.
Okay, so if anything went wrong, you're in the lab, you want to explain the source of that errors. Those errors. Okay, like for instance, there are a couple of you guys that Mentos didn't make it quite in the bottle, right? They hit the floor beforehand or they hit the floor afterwards, right? So then that would be an example of something that went wrong. And if you didn't repeat the experiment, like sometimes we have a lot of resources that you can repeat the experiment, sometimes we don't, right? Or time, we don't have enough time to repeat. Your experiment blew up. This one did, but it, not quite the way that we wanted it to blow up in this case, right? But let's say it was an unexpected blow up, so you didn't get a chance to get the results from that. So then you would explain, this is what happened in that experiment, right? Kind of gives you a body, right? Okay. Now, again, things are gonna go wrong sometimes, right? It's okay. Don't worry about it. Don't cry over it. You're not gonna get murdered, right? As long as you include it into your conclusion. Right? So, in your own words, explain something, one thing that you learned, right? You learned many things, great, but I just want to know one thing that you learned. What was one thing that you guys learned from this? Well, I learned not to drink Mentos or not to eat Mentos and soda at the same time, right? That's what I learned from it. So name one thing that you've learned. So the idea is that, remember, at the end of the day, you need to learn at least one thing before you finish this class. Okay, one thing. The last thing is, this is that part. I know some of you guys wanted to send me videos. I love the fact that you guys want to send me videos, right? But this is where I want you to put that video link, right? Okay, so every time that you guys do your formal lab report, you have the opportunity to get the extra credit points. Here's an opportunity for those. Questions? Yes.
Do you want the lab report like in certified format? Like
MLA would be fine. Typically in science, we go with, actually, let's see, there's two different major. I'll actually see you guys. So you guys can MLA is fine. I'll accept it. Any other questions? Any questions?
For the extra credit, is there any specific way you want us to do it?
I would like you to either have it on YouTube, or have it on Insta, or let's see, Snapchat, what other social media? TikTok, any of those, you can put on any of those as long as I have a link that I can click on to get there. So it matters.
The video link, is it just pretty much like doing everything but in the video? Or
Yeah, it's doing parts of your experiments through the
Oh.
video. It doesn't have to be the whole thing, because that could be, sometimes those experiments will take all day long. Questions? Concerns? Cash?
Can we get payments from it? Or we just split it? Or...
Yeah, we'll split it. Hell yeah. I'm not opposed to sharing money that I never had before, I'm all for it. Okay. Okay. So, how many people got their laptops? So, before we do our laptops, we're going to talk a little bit about dimensional analysis so that we can actually do the lab, and then we'll do the lab right up towards the end. So that we can kind of do everything in one day. Okay. So we're going to do a whiteboard talk on dimensional analysis because it's in my lecture, but it's a little more deep in my lecture. But I want to get us to it so that we can actually start working on it. Okay. And then we'll also talk about safe things. I'll just, yeah, I'm getting there. You're great. My computer keeps trying to update. So how many of you guys have heard of dimensional analysis? Got one. Anyone else? Okay. So dimensional analysis is basically following units. So when we think about when we think about measurements or data, quantities, right? We usually have what we call quantities and a unit to let us know what you're measuring, right? So if I told you 5, okay, you guys have 5. Right. What does that tell you?
5 days, 5 hours, 5 minutes.
5 years, 5 months. Right? This is doing 5, right? So you have no idea what that I mean by 5. So I have to tell you a unit that's associated with it. You have 5 minutes to get your butt in that chair, right? So that means you got 5 minutes to get in that chair, right? 5 minutes is what? Right? I would probably say 5 seconds. It would make more sense, right? Okay. So we put a quantity and a unit that's associated. Okay. So when we're talking in science, most things have units, unless it happens to cancel out. Okay, we'll talk about that here soon. I'll move around a lot, so gotta keep focused. Okay, so time. What are units of time? Seconds, minutes, hours, days, years, months. Okay. Okay. So we have conversions that we've known our entire lives since we're like this high, right? How many seconds are in a minute? 60. 60 seconds equal 1 minute. How many minutes are in an hour? 60 minutes equal 1 hour. How many seconds are in a year? Come on. Should you know that? A million. Well, we can calculate, right? So if I started out with 1 year, what I can do, I can actually go through what we call dimensional analysis, using those units to help me get to the point that I want. I want to know how many seconds are in a year. So I want to end up with seconds. Okay? So what are some other conversions that I know about a year?
Days.
How many days are in a year?
365.
365 days in 1 year. So I can use this as a conversion factor. 1 year, since I'm starting off with a year, I want to get rid of the year. And now I have 365. Okay. So if I have days, how many hours are in a day? 24. So 1 day equals 24 hours. These units are going to cancel out. How many hours are, or how many minutes are an hour? Hours are going to cancel out. And then how many seconds are in a minute? 60. Minute. 60 seconds. So minutes. So who's going to do the hard math for? So when we're looking at this, all the numbers up top are going to be multiplied, and then you're going to divide it by numbers on the right. We look at it, it's 1, 1, 1, 1 at the bottom. So all we have to do is multiply all the numbers up.
31.536 million.
So 31.1
536.
536. You said million?
Yeah.
So that's a whole bunch of seconds, right? Okay. So this is an example of dimensional analysis. Not too hard? Okay. So where we're starting with one, in this case, we're starting with 1 unit, now we're converting to another. Okay. So a lot of times we get word problems where we're talking about, let's say, for instance, gas mileage or something like that, right? So if I drive 90 miles per hour, right? Everybody get this down? I write there. I caught it fast. Okay, match it down. $95 miles per hour. Let's see. I'm driving for 3 hours. How many miles?
$165.
Okay, how did you calculate it?
Multiplied it by 3.
Okay. So we set it up. Our given 3 miles and 3 hours. 3 hours. Here our conversion is for every 95 miles, that's going to be 1 hour. You said you had what?
Wait, I was off 285. But where I got the extra 20 from?
Just adding the extra, right?
Yeah, off the head, but no.
So he was taking that route to his side piece house before. Okay. So again, you're getting rid of those units to get the units that you want. That's dimensional analysis. Not too hard? So let's see if we can make it a little more challenging. You guys have 5 questions. We got this, 10 questions. So we're going to kind of go through this together. If you guys don't mind. I mean, if you do it by yourself, you want to, but you guys want to do it, we'll do it like this. You guys can work in your groups, right? Discuss with your groups, and then we'll start and do it as a group together. Okay. Yeah. So that means you guys have to discuss. I want to hear things. You can't just be working on your paper by yourself. Okay? Dustin.